Alright guys, welcome to part 2. So we're going to start by talking about Lewis structures of ions here. So we follow pretty much the same steps drawing Lewis structures for ions. We count up the total of the valence electrons and then we arrange the atoms and we put in bonds, blah 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 blah, we check the total. The only difference is that obviously an ion has a charge, so we have to consider the charge when we're totaling up those electrons. In the case of anions, meaning ions with a negative charge, we increase the total number of valence electrons by the amount of the charge. And then if we're dealing with a cation, something like ammonium, which has a positive charge, we actually subtract the charge from the number of valence electrons. That's what would give us a positive. So an example of a polyatomic anion is the phosphate ion. So PO4 with a 3- charge. So I want you to take a second, maybe pause the video and see if you can figure out what the total of valence electrons would be on that. And if you paused it, then hopefully when you total these up, you got something like this. Okay, 5 electrons from phosphorus because it's in group 15. And then 6 electrons from each oxygen because it's in group 16. And then we add 3 additional electrons because of the charge on the ion, giving us a total of 32. Okay, and then we're going to use that information to see if we can work out the Lewis structure for the phosphate ion. Now, everything's not going to animate in quite the same as it did be on the previous slides, and I'm not going to go through all those exact same steps in text on the slide, but the ideas are all still the same. So I've got my total valence electrons, then I'm going to arrange my elements in a logical way. Phosphorus is less electronegative than oxygen, so I'm going to put it in the middle. And I'm going to arrange the oxygens around it, and then I'm going to put single bonds between all the adjacent atoms. And then I'm going to fill everything's valence. So that means phosphorus already has a full valence, but each oxygen needs 6 more electrons to get a full octet. Looks like that. And then I'm going to check my electron total. And I can see that there's 8 electrons around each oxygen, so that gives me a total of 32. Everything's octet is satisfied, so my represented electrons match my total valence electrons, which means my Lewis structure is good. The last thing I need to do, because it's an ion, I'm going to put these big square brackets around it, like you see right here, and then I'm going to show what the charge is just outside those brackets. That's it. Okay, so just a couple changes with the total of the electrons and then showing the charge on my final Lewis structure once everything else is good. Okay, so here's a second example, and I'm going to recommend once again that you pause the video on this slide and just try figuring out the Lewis structure for the nitrite ion on your own. So welcome back. If you did take a pause, let's see if what you wrote down is the same as what I've got for my answer here. So you should have 18 total valence electrons, and we're going to put nitrogen in the middle. And we're just going to arrange our atoms just like that, pretty straightforward, and then fill up the octets if necessary. And then I'm going to count my electrons. Right now, I have 20 electrons, which is too many. So I'm going to, I went maybe a bit too fast with that. So I'm going to erase the non-bonding pairs on 2 adjacent atoms, and then I'm going to replace that with a double bond. Okay, and then I've got my square brackets around there, like this, and I'm showing my charge, and now that I've put that double bond in, I can change this total to 18. I've got the correct number of electrons now. Okay, these next couple slides will highlight something that actually, I didn't point this out when we first drew the structure of carbon dioxide, but we actually didn't, we drew it the right way, but there's actually more than one way I could have drawn it, following all the rules that were on that slide. So obviously this is what I did draw, but to get the correct total of electrons, I could have done one single and one triple bond, or I could have had that triple bond on the other side. Okay, so we're going to talk here about a set of tools we can use if there's more than one option for a Lewis structure, a set of tools we can use to pick the correct Lewis structure. Okay, and the tool that we're going to use is called formal charge, which is a way of calculating sort of what the charge would be on an element in a molecule by comparing the number of valence electrons that it brought with it to the number of electrons that are assigned to it in the diagram. Okay, so there's an example of this over here. And I'll sort of break down on what happened here. So it's easy with carbon dioxide because it's a linear molecule, so we can line everything up nicely here. But if you have sort of a molecule that's more distributed around a central atom, then you can always sort of do the formal charge calculation just right beside each atom, sort of fitting them in small. That's usually how I do that. So we know that each oxygen always brings 6 valence electrons with it, so that's easy to fill in. It's just looking at the periodic table for the group number like I've been doing. Okay, then I want to figure out the number of electrons assigned to the atom in the diagram. And the way I calculate that, if there's a non-bonding pair, both those electrons count. And if there's a bond pair, then I only count 1 electron from the bonding pair. Okay, so right now oxygen has 2 here and 2 here. That gives me 4. And then I count 1 from each bond. So 4 plus 2 gives me 6. And then I find the difference between those values, valence electrons minus assigned electrons in the diagram, and that gives me the formal charge. Okay, so in this case, the formal charge is 0 on this oxygen. I do the same process with carbon. I look at carbon only has bonding electrons around it. It's got 4 bonds around it. I count 1 electron from each of those bonds to give me 4 assigned electrons, and I also remember that carbon is in group 14. It brought 4 valence electrons, and then my formal charge is 0. And then this oxygen is the same. It looks the same as this oxygen, so hopefully you can see why I would have 6 and 6 again here. Now this other version of the Lewis structure, you'll notice this is totally fine according to the rules that we laid out before. Oxygen's octet is satisfied, it's got 8 electrons around it. Carbon's octet is satisfied. And this oxygen, even though it looks different from this oxygen, it also has its 8 electrons. Similarly, carbon dioxide is allowed a total of 16 valence electrons, and that is the case here. I've got my 16 valence electrons represented. So it's not breaking any of those rules. However, if I examine the formal charges, this oxygen brought 6 electrons but has 7 assigned to it in the diagram, giving it a formal charge of -1. Carbon is still 4 and 4. It's fine like this. But this oxygen over here, it brought 6. It's only assigned 5, so it has a formal charge of +1. So when I'm comparing possible Lewis structures, I want to look at the formal charges and I want to select the structure that has the fewest formal charges. So if I look back at the example we just did, I can see that this version of the Lewis structure has formal charges of -1 and +1 over here, whereas this one has no formal charge on any of the atoms. So that's why this is the Lewis structure of carbon dioxide that we use most often rather than this one. Okay, this is the much better fit because it minimizes formal charge. Okay, so I've got another example here with this slightly more complex, the cyanate ion. So I want you to take a second and try, pause the video, give a try to assigning formal charges. See if you can work that out. Okay, so welcome back. And if we take a look here, those are the formal charges, so hopefully that's what you got. And that actually means that I can definitely eliminate one possibility here, right? This one definitely has too many formal charges, so I can get rid of that as a possible Lewis structure. It doesn't minimize formal charge. But then I look over here, these two possibilities both have the same formal charge. Okay, and you'll notice when you have an ion, you're always going to have some formal charge. Okay, you can't have zeros across the board and then have an ionic charge on the whole molecule. So then I need to go to this second point. Oops. I got a little trigger happy with the mouse there, but I'm going to go to the second point. I'm going to select the Lewis structure that puts a negative formal charge on the more electronegative atom. So I can either, in this structure, I have a formal charge on nitrogen. In this structure, I have a formal charge on oxygen. I'm actually going to go with this as my correct Lewis diagram because oxygen is farther to the right of the periodic table than nitrogen. I know it's more electronegative, so I'm going to assign the negative formal charge to oxygen if possible. So that's the most correct Lewis structure. Okay, I'm actually going to pause the video there, and then part 3 will deal with situations where multiple Lewis structures are all equivalent.